Hey everyone, welcome back to the channel. Today, we are taking a deep dive into the life and mind of a true giant of science, Sir Isaac Newton. You've probably heard of him, the guy with the apple, right? Well, there's so much more to his story, and his discoveries are still shaping our world in ways you might not even realize. So, why do Newton's laws, formulated over 350 years ago, still matter so much today? Let's find out. To really understand Newton's genius, we have to go back to his beginnings. He was born in 1642 in a small village in England. His childhood wasn't easy. He was born prematurely and was so small, no one expected him to survive. His father died before he was even born, and when he was 3, his mother remarried and left him in the care of his grandmother. You can imagine how lonely that must have been. He was a quiet, introverted boy, often described as solitary. He wasn't a star student at first. In fact, he was often at the bottom of his class. He preferred to spend his time building things, intricate models of windmills, water clocks, and even a little four-wheeled cart he could steer himself. He was a tinkerer, a builder, an observer. He was fascinated by how things worked. A turning point came when he got into a fight with a school bully. The story goes that Newton, though physically smaller, was so determined that he won. But it wasn't enough to just win the fight. He decided he had to beat the bully academically too. This competitive spark ignited something in him. He started applying himself to his studies with incredible focus, and soon became the top student in his school. This little story tells us a lot about his personality. When faced with a challenge, he didn't just meet it, he aimed to dominate it. It's a powerful lesson, isn't it? A moment of conflict pushed him to unlock his own potential. His mother, at one point, pulled him out of school to become a farmer. Can you imagine a world without Newton's discoveries because he was stuck plowing a field? Thankfully, it was a disaster. His mind was clearly elsewhere. He'd be found reading books under a tree instead of tending to the sheep. His old headmaster saw his wasted potential and convinced his mother to let him return to school to prepare for university. It was a crucial intervention. He went on to Trinity College, Cambridge, where his real journey began. At Cambridge, Newton immersed himself in the works of the great thinkers of his time, people like Galileo, Kepler, and Descartes. He was a voracious reader, filling notebooks with his own thoughts and questions. He wasn't just absorbing information. He was challenging it, testing it, and building upon it. Then, in 1665, a major historical event changed everything: the Great Plague. Cambridge University shut down, and Newton was forced to return to his family farm for 2 years. For many, this would have been a setback. For Newton, it became his year of wonders. Free from the structured curriculum of university, his mind was completely unleashed. It was during this period of intense, isolated thought that he laid the groundwork for his most famous discoveries. This is where the famous apple story comes from. While it's probably a bit of an exaggeration, the idea is that watching an apple fall from a tree made him wonder, if gravity pulls an apple to the ground, could that same force extend all the way to the moon? This was a revolutionary leap in thinking. Before Newton, people believed the heavens and the earth were governed by different sets of rules. Newton proposed a universal law of gravitation, that every particle of matter in the universe attracts every other particle. It was a single, elegant equation that could explain both a falling apple and the orbit of the planets. But that wasn't all. During this same period, he developed the fundamental principles of calculus, which he called the science of fluxions. He needed a new mathematical language to describe motion and change, so he invented it. He also conducted his groundbreaking experiments with light and prisms, discovering that white light is actually a mixture of all the colors of the rainbow. Think about that. In just 2 years, working mostly in isolation, he laid the foundation for classical mechanics, calculus, and modern optics. It's an almost superhuman burst of intellectual creativity. After the plague subsided, he returned to Cambridge and his career took off. He became a professor and later published his masterpiece, Philosophiae Naturalis Principium Mathematica, or just the Principium. This book is one of the most important scientific works ever written. In it, he laid out his 3 laws of motion. Let's quickly refresh them. First law: an object in motion stays in motion, and an object at rest stays at rest, unless acted on by an external force. This is the law of inertia. Second law: the force acting on an object is equal to its mass times its acceleration, or F equals ma. This is the one you probably remember from physics class. It's the engine of classical mechanics. Third law: for every action, there is an equal and opposite reaction. These laws seem simple, but their implications are profound. They provided a complete, deterministic framework for understanding the physical world. For the first time, the universe could be seen not as a place of random, unpredictable events, but as a giant, intricate machine operating according to precise, knowable laws. This was a monumental shift in human thought. It gave birth to the Enlightenment and the idea that reason and observation could unlock the secrets of the universe. So, that's the history. But the big question is, why do these laws from the 17th century still matter? We have quantum mechanics and relativity now, right? Well, yes, but Newton's laws are far from obsolete. For the vast majority of our everyday experiences, they are incredibly accurate and incredibly useful. Think about engineering. Every time you see a skyscraper being built, a bridge being designed, or a car being manufactured, Newton's laws are at the core of the process. Engineers use F equals ma to calculate the forces and stresses on structures to ensure they are safe and stable. They use the law of inertia to design engines and braking systems. The third law is essential for understanding everything from the recoil of a gun to the propulsion of a rocket. You can't launch a satellite into orbit without Newton. The trajectories of spacecraft, like the Voyager probes that are now in interstellar space, were calculated using his laws of motion and universal gravitation. Let's talk about transportation. When you're in a car, the friction between the tires and the road, the acceleration you feel when you press the gas, and the force needed to stop, it's all pure Newton. When an airplane FLIs, the lift generated by the wings must overcome the force of gravity, and the thrust from the engines must overcome air resistance. Again, it's a beautiful, real-world application of Newtonian physics. Even in sports, his laws are everywhere. A baseball player hitting a home run is a perfect example of F equals ma. The force of the bat applied to the ball for a short period of time creates a massive acceleration. A figure skater pulling in their arms to spin faster is demonstrating the conservation of angular momentum, a direct consequence of Newton's laws. Understanding these principles can actually help athletes improve their performance. But what about the modern physics of Einstein and quantum mechanics? Don't they prove Newton was wrong? Not exactly. A better way to think about it is that they refined his work. Einstein's theories of relativity are needed when you're dealing with objects moving at very high speeds, close to the speed of light, or in very strong gravitational fields. Quantum mechanics is needed when you're dealing with the subatomic world of particles. But for the world of medium-sized objects at normal speeds, the world we live in, Newton's laws are a fantastic approximation. They are a special case of these more general theories, and they're a lot simpler to use. You don't need to use general relativity to calculate the trajectory of a thrown basketball. Newton's laws work perfectly. Beyond the practical applications, Newton's legacy is about a way of thinking. He showed us that the universe is knowable. He demonstrated the power of the scientific method. Observe, form a hypothesis, test it with experiments and mathematics, and refine it. His success was born from relentless curiosity, an unwillingness to accept that's just the way it is, and the intellectual rigor to back it up with evidence. He was a master of breaking down complex problems into simpler parts, solving them, and then putting it all back together. The lesson from Newton's life isn't just about physics. It's about the power of focus, the importance of curiosity, and the idea that great breakthroughs can come from periods of quiet contemplation. His story shows us that challenges, like his difficult childhood or forced quarantine, can become opportunities for incredible growth. He teaches us that a single, powerful idea can change the world. So the next time you see a plane in the sky, or lean back in your chair, or even just watch something fall to the ground, take a moment to appreciate the invisible laws at work, the laws gifted to us by the brilliant, complex, and enduring mind of Isaac Newton. They are the silent, powerful engine of our modern world. Thanks so much for watching. I hope you found this journey into Newton's world as fascinating as I do. If you enjoyed this video, please give it a thumbs up and subscribe to the channel for more deep dives into the history and science that shape our lives. Let me know in the comments what you think. What is the most surprising thing you learned about Newton today? Until next time, stay curious,